Well, hello. Wuso here. Let's continue this discussion on simple harmonic motion. In this video, I'm going to bridge the gap between simple harmonic motion and circular motion, and then subsequently waves. And this is where I think it starts getting kind of cool. We've got this mathematical model that we're going to develop. And it should make sense. And there's not a lot on this screen, but I'm going to try to spend a lot of time explaining what we're seeing here. So this first video, this comes from this pretty cool website, it's carleton.edu. They do what they call direct motion videos, and they slow it down. You can go frame by frame and look at a lot of stuff. I encourage you to go to their website to check out many more physics videos. This particular video, I'm not going to slow down for you. I'm just going to show you it to kind of show how we can model simple harmonic motion to be very much like uniform circular motion. And so what we've got here is we actually have three different things that are going to be undergoing oscillatory motion. We're going to have this pendulum up here that's going to rock back and forth. At the exact same time, we've got this mass spring system that goes back and forth. This is a pretty simple setup. We've got a spring here and a spring here. This would more or less be equilibrium. We're going to move it this way. The one spring's going to pull it back this way, and then as it pulls it back, the other one pulls it back, and it will just go back and forth. And then down here we have a rotating platform that's going to rotate around, and what this person's going to do is toss this film canister, I believe, of some sort right on here so you can see it going back and forth. And I'm going to talk about this a bunch, and what we're going to try to do is plot some information here conceptually. We're not going to use numbers, and then I'll talk about all that jazz over here. So let's watch this and see what we're looking at. It's pretty cool because what ends up happening is it goes in simple harmonic motion, but everything will have the same period. Give me 1 second, I got to fix something. Alright, I think I fixed it. Let's watch. Okay, I did. So you're going to see them set the pendulum and the spring in motion. They have the same period. And then if he times it right, bam. And so then, yeah, you see that? Everything's got the same period of motion. It takes the same amount of time to do one revolution on the platform as it takes to go back and forth on the spring, and as it takes to go back and forth on the pendulum. This is mesmerizing. I can look at this for a while. I'm going to let this play out, and then we're going to play it again. I'm going to try to take some not data, but some conceptual information from this. So once again, we've got this system going around. And what I'm going to first do is I'm going to mark the extremities, the extreme ends. And I can write right on this. That's the fancy part about this. I'm going to make, this is going to be one end. This will be another end, right? And right in the middle here, roughly here, is our equilibrium position, okay? This is going to be positive x. Now, this is the largest possible value x will get. So not only is it positive x, but we're going to call it the amplitude because it's the largest possible value it will get. So this is positive a, which we can say is simply equal to x. Here is going to be negative a, which also is equal to, in this case, negative x. Then here, x is going to be 0. It's going to be my equilibrium position. So we're going to have this guy going from positive A to negative A, positive A. The pendulum will be doing the same thing. And then although the object on circular motion goes deep, goes in 2 dimensions, it'll be traveling left and right from positive to negative anyhow. Sure, it goes forward and back as well in that y dimension, but let's just pay attention to its x motion as this platform rotates. Not only that, we're going to talk about where the object is when we begin time. And to make things nice and simple, I'm going to wait until it gets over here. And I'll pause it when I get there and kind of explain to you what I'm talking about in a second. So let's let this go. And let's see if I can time this as well as he does. Pause. Okay, cool. I nailed it. I'm so proud of myself. Okay, so here's where I'm going to now technically begin time. Just for giggles here, we're going to talk about the object, and I don't care if we want to talk about the spring, the pendulum, or the film canister. Where is it at the beginning moment in time? And where it is in the beginning moment in time is just somewhere in the positive region that we're going to call A. Alright? Then, it's going to start to travel back towards the equilibrium spot. And I want you to think about this. If we want to map the entire down and back motion as one period. Remember, t is period, which is the time for one cycle. And I'm going to call this the beginning of time. So the time for one cycle is go down and back, right? As it goes down, how many revolutions later is it by the time it gets to the equilibrium the first time? Think about that. Here's where it is in the beginning. We'll talk about the mass. I think that's the easiest to show. Then it goes here, 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 and here. Is it fair to assume that this is a quarter of the entire cycle? Let's unpause it. No, I didn't quite hit it that time. I don't think I can step back. No, I can't. Shoot. All right. Sorry, patience here, right? Patience. It's going to go down. Goes down and pause. Oh, hey, not too bad. I kind of nailed it. So, a quarter of a cycle, it's at the equilibrium position. Okay? So if I were to break this down into, here's the quarter mark. I'm just going to go random here. Half mark, right about the same. 3/4 of a cycle. Here, right here is what I'm going to call one entire period. I don't know the time, the amount of time that is, but I know that I'm going to call that T. So at this spot, so in the beginning the object was here, and now the object is here. Right? A quarter of a cycle. Halfway through its motion, so it started here, quarter, halfway is going to be down here. Where are we? Yeah, we're at negative x. Negative x is the same distance away on the other side of the x as, wrong color, purple. So here's negative a in the negative part of the graph, and that's where the object will be halfway through the motion. And I'll unplay it in a second. We know, okay, quarter, half, 3/4. That 3/4 that's on its way back to the right here. And then finally, after one entire cycle, it's back up here. Let's play this. Cool. Back and forth. Back and forth. And if I knew the time for one cycle, I would be able to tell how much time went by after 2 cycles, 3 cycles, 4 cycles. Heck, I can even do in between 4.1 cycles, 2.7 cycles. I should be able to determine the amount of time or where it is in its path at any point in time. I'm going to come back to this. We're going to unpause this in a minute. Now,